Hmm. Okay, so I will start now. So good morning, and today is 33rd lecture. Of course, there were many 1.5 hours, 1 hour. So this is 1 hour. So let's consider a problem. I think yesterday I finished torsion. So of course, that is not all that is there in the torsion. I have covered only the basics. Now it is left to you to read on your own. So that is, I have given you only some simple examples of how to solve torsion problem from theory of elasticity point of view. Now let us take a simple problem of which you have already done, beams under pure flexure. When we start bending of beams in strength of material course, first course on solid mechanics, we start with this, that let there be a beam which has a vertical plane of symmetry. So z axis, that means xz plane, this is xz plane, this is xz plane, x is coming outside here, this is the cross section, this is the cross section, this is the longitudinal section. So if this is the cross section, so xz plane is a plane of symmetry, it divides the total cross section into two halves, and then all the loads are applied in the plane of symmetry, so that we have only bending, not twist. Otherwise, if there is no plane of symmetry, if you do not apply load here, then it will, I do not want that. So, in order to avoid that, all loads are applied in the plane of symmetry. Anyway, beam problem, as I have told you earlier also, that it is a case of pure plane stress problem. From theory of elasticity point of view, it is a plane stress problem, two-dimensional plane stress problem. So, it is a 2D. So, if you can solve the 2D problem, yes, it is okay. I mean, then you have solved the exact problem, but then 2D problem has certain limitations. I mean, certain difficulties in solving. There is some mathematical. So, we say that yes, this is my beam, and it is subjected to pure bending. Pure bending means what? Yes, there is no, every cross section is only subjected to, there is no change of moment, because shear force is given by always dm by dx, rate of change of m with respect to x is shear force, plus minus depending upon the sign. This is dm, this will be all right if you take v upwards. So, anyway, plus minus depending upon what sign convention you take. So, there is no change of moment. So, moment is constant throughout, and then we study. So, this cross section becomes, after bending, this cross section becomes something like this. This bends, and then it has a center of curvature here, and we do some geometrical line. So, anyway, the basic assumptions that we make in beam theory right in the beginning, we always make an assumption. One, the beam is slender. The other one that we make is that this transverse cross section which is there, this one is transverse cross section, this one is one cross section which we call transverse cross section. Normal to x axis is transverse cross section in z direction. That remains plane, see this diagram is plane. So, this remains plane, and So, after deformation the shape of this has become something like this. So, it remains plane and neutral axis also, this the centroidal axis also bends. So, and maintains a 90-degree always with the neutral axis. So, this angle is always 90, this angle is even after bending it is 90, before bending also this was 90. Therefore, what is does mean? That shear strain in which plane? Xz is 0. Xz, if you take, you draw shear, x is this, z is upwards. So, this xz always 90 degree is maintained, this one. Xz plane shear strain is 0, not shear stress. So, and there is one more, and the length, so and the length of the normal does not change during deformation. This length, whatever length is there h, this length, and afterwards this length, this, because normally something will happen, it will undergo some change. So, but then we are saying, you know, this also is h. So, one is gamma xz is 0, second one is, because the length does not change, so we also say epsilon z is 0. In words, this means that plane sections, transverse plane sections remain plane and normal to the neutral axis, and the length of the normal does not change. So, that is the in words, but in mathematics this is what is its meaning. And third assumption, so this is called, this assumption is called, by the way, in fact only this one is called Kirchhoff assumption, Kirchhoff Kirchhoff hypothesis, not assumption. He made a hypothesis. So, he said that yes, my hypothesis is you make based upon physics. He said if the beam is very slender, that means this first one is there, h is very small compared to length, then whatever I am making is right, more or less. So, this is assumption. So, this is called Kirchhoff hypothesis. And the third one we make, that see, there is a pure bending, this normal stress in thickness direction. What is that normal stress? Means if you take this small element here, how will you show normal stress in thickness direction? It is this stress. What is the name of this stress? Sigma z. What is the name of this stress? Sigma x. So, sigma z, we also say that sigma z is very small compared to sigma x and other stresses. Of course, in this case there is only one and other stresses. The meaning is this, in mathematics how do you take care of this, is that sigma z is considered small, not equal to, but it is small, and in the constitutive relation wherever sigma z comes, we make it equal to 0 compared to other stresses. Wherever you have constitutive relation sigma x, sigma y, sigma z, so we will say this is small compared to, so that term will neglect. So, with this we come up with so I have already, many things I have already told you, that it is a prismatic cross section. Prismatic means constant cross section, and it is composed of isotropic and linear elastic material, and this load is acting in the plane of symmetry. So, this I have already told, and then I will try to now differentiate between this strength of material approach, which we call, I am calling strength of material, which is based upon assumption. Assumption we have already made 3 assumptions, 3 or 4, sometimes we also put this separately, we do not put it. So, there are 4 assumptions or 3 if you want to put it in one sentence. So, this assumption we develop the theory and we come up with this. We come up with this formula. This is a very famous formula, that yes, longitudinal stress equal to m moment multiplied by this distance z, which I had shown here also. Z is this z, where this one I have shown it here now. So, at any point z, so and then divide by moment of inertia. All other stresses are 0 under pure bending. So, sigma y is 0, sigma z is 0, tau xy, all the 3 shear stresses are 0. So, except one. Of course, this will cause strains, and we can find out from the Hooke's law what will be the strain, sigma x by E. So, this is mz by I E. But other strains will be there. See, although stresses are 0, epsilon y, epsilon z is there. So, epsilon x is there, then epsilon y will be nu times this. From the Hooke's law only it will come. From the Hooke's law it will come that it will be nu times this. So, it will be nu times mz by I E, and all the shear strains are 0. So, this is the state of stress and strain when you subject a symmetric beam, with pure bending. And we start our bending theory with this. First, we never say that load is applied, any load. We always, the first introduction, I mean, if the teacher is saying that no, it is under load, then that means he has not understood. It is a special load, it is pure bending only. So, the theory that is developed and which gives you this formula is under pure bending. I will show you that this formula under pure bending is, although we have made so many assumptions that beam is slender and this and that, even in the case of, even if the beam is not slender, and this satisfies all the equations of the elasticity, 2-dimensional elasticity, plane stress if you take, everything is satisfied. So, this is, that means this is the exact solution even for short beam. Even for short beam, because once you solve, I mean, once you have learnt now theory of elasticity. So, what is there? You test, you have got the state of stress. So, you will find you have got 3 equilibrium equations. First, you have got 3 equilibrium equations. You will see that equilibrium equation is satisfied. Equilibrium equation is satisfied, this distribution. If you take, write down all the 3, 0 equal to 0 on both sides will come. There is no, of course, without body force. So, this one is satisfied. Now, strain field, once you know that stress is okay, then you should also check the strain field, and for checking the strain field you should see compatibility. Now, compatibility also is satisfied. I mean, I do not want to write the 6 equations and show you, this is also satisfied, compatibility. So, this also is satisfied. And finally, it can be seen, I mean, that stresses also satisfy the boundary conditions. Boundary conditions means the distribution of stress at the end must be equal to the moment applied. So, thus one gets exact solution for the pure bending case of beam, even short or slender, long or short, I mean it doesn't matter. So, this formula is not bad, although we have used assumptions, but this satisfies all the equations of you can check, and so this is exact. Then I will show you how long, I mean for what loading it remains exact. It is not for every loading. Pure bending, yes, there is no problem. Now we take bending with shear, that means there is some change of bending moment. Is it okay? Same problem. Now we have added shear. Shear means there is some distribution of load, so that you have some. It can also be constant shear. Bending plus shear, bending moment plus shear. Anyway, this formula, so this is this you must be knowing that this is called Bernoulli-Euler formula or Bernoulli-Euler beam. This formula was derived by Bernoulli and later checked and reconfirmed by Euler around 1700 something. So, it is very old. It is Bernoulli-Euler formula, and then we know this is okay. We also derived during the course of our derivation that 1 by r curvature equal to m by ei. Of course, this moment is about, I am just clarifying, moment is about y axis. Moment of inertia is also about y axis in our case. So, you should know sigma y sigma z is 0, sigma x is equal to E times epsilon x, and I can write sigma x equal to E times epsilon r equal to E times du by dx. So, therefore, sigma x or du by dx will be m by z, I mean m by mz by I divided by E. I have put here E because sigma x equal to E times. So, if you equate these two, this equal to this, so you will get mz by ei equal to du by ds. Now, this is our equilibrium equation in x direction. So, let us go through the derivation. So, here I did not write, see I have written here, let us say the first equation of equilibrium. Now, this one is known, you have already got in terms of displacement, we do not know this. So, this again I am writing here, yes, this is equal to this, and then this is your relationship between the stress and displacement. Stress by using constitutive relation and displacement. So, these are your, and then now I am substituting this all the three, this one, then this one and this one in stress. So, first term is this, second term will be this with respect to y, this is with respect to y. So, equal del square u by dy square, here del square v by dx dy, and similarly this one will be with respect to z. So, del square u del z square del square w dx dz. So, this is your equilibrium equation. This of course, this I always, because we have used already displacements and we have derived strains from the displacement. So, there is no question of using compatibility equation. Compatibility equation is used when you start with stresses, we do not start with displacements. So, that is what I have written. So, there is nothing to worry about compatibility relations. So, anyway, this you simplify this, I have done some simplification, there is nothing, whatever is function of x, keep it, z is not a function, I is not a function of x, I is constant, we have taken prismatic. Moment, yes, moment because with shear, now we are talking of moment with shear, na? I mean sorry, so it will be changing with respect to x. So, this has to be put in the derivative. Then here g times I have put all the 4 derivatives inside the bracket, z by ei. Here I have added one term and I have added one subtracted one term. So, this one is del square u by delta x square is subtracted and del square u by del x square is added. Now, you will say why these are the ways of manipulation. In olden days, people had lot of time. Nowadays, researchers will not do this. Once they got here, I will compute it directly. In olden days, there was beauty in deriving a neat expression, because there was no computers. So, analytical solution was given lot of emphasis. So, these people spent months, years to derive a simple and compact relation. So, by doing this, I do not know who did it, but then this is what is. So, this is the same expression, first equation of equilibrium equal to 0. So, if you take this, then we have got this Hooke's law. These are our strain Hooke's law. This is just I am saying. So, if I sum all this, why I am putting this here is, now this one is nothing but epsilon x, epsilon y, epsilon z. This is the strain invariant. This is the strain invariant term. So, I am just trying to find out what is the. So, this can be found out from the elasticity, and there will be some relationship. You go through manipulations and okay, there are many things that can be done. 2g by lambda. Now, you know lambda is a Lamé constant. Lamé constant is again related to E and nu. So, this is, it can be written like this. I will only give you some relationship between lambda, because lemma has been used. So, lambda is called Lamé constant, which is a function of Eg, I mean 2 other constants. These are the various relations which are available, which can be derived. So, lambda can be like this. In terms of E and G, it is this. In terms of G and nu and E, all the 3 are there here. E, nu and G, everything is there. Only 2 are independent. And because we know this G equal to this, and this one is between lambda, G and E, E, G, lambda, okay, something. And then this one is between lambda is here also, G, E and nu. E, G and nu, all the 3 are there. So, it is similar to E, nu and G, all the 3 are there, okay. So, these are some relations of that can be derived. So, this one finally we get this. If you sum all this, it is. Again you will say, why did I write epsilon x in the left hand side again on right hand side, and there is a reason for simplification now. So, if you do this, go through all this, so it can be derived as this, and therefore, the strain invariant equal to 1 by lambda sigma x equal to mz by I minus 2g by lambda epsilon x du by dx. So, then I am saying replacing the last bracket of our equilibrium equation by the right hand side of this. This is the right hand side. So, please replace this one. So, I am only replacing this, the last one, by this. First bracket is remaining same. If you do this, now dm by dx will come here. There is already dm by dx here earlier. So, here also there is a dm by dx. So, now you collect all the terms dm by dx, and del square u is there. Del square u will come here also, this and this. So, these two can be combined to get this, and then you are left with 1 2 del square u dy square, del square u dz square, and g is taken on the right hand side. So, you get this. So, there is nothing except that you have to do algebraic manipulation, because we want to prove something. I will tell you what. So, this is equal to dm by dx, this is remaining the same. Where did g get? I have divided by g throughout, by the way. G is divided throughout, G has come here. So, G, yes, this is okay, and here, so this is okay, this bracket remaining the same. And this is right hand side. Why did I repeat this, by the way? Tell me, why did I repeat this? You see, this one has been written as del upon del x, and again del u by del x. Del u by del x is epsilon x. So, epsilon x is this. Yes, lot of manipulation, just to prove. So, they had so much of time and energy, people, our erstwhile scientists and engineers, that in order to see that what is happening, yes, then finally you get this. So, this one is there now. So, now del m by dx will come up one more here also derivative of m is there here. So, now these two terms are combined, and you get here this. Incidentally, if you take z outside, all these are only elastic constants and moment of inertia. So, these are all constant. Yes. Then I am again, what is epsilon x? This. If you integrate this, du by dx equal to mz by ei. So, if you integrate this with respect to x, so you will get z by ei integral m dx plus some constant psi. This psi or chi, no, this is kappa, actually this is kappa, this like this is straight line, this is curved like this, it is kappa, but it is a constant here, it has to be function of y and z. And if I take the derivative of this with respect to, because this one is derivative of this with respect to y and this is with respect to z. So, if I take with respect to, because this is a function of y and z, this is only a function of x, by the way, and z. I am taking with respect to y. So, this will become 0 plus del kappa by del y. Second derivative will become this. Similarly, second derivative with respect to z will become this. So, right hand side can be written in terms of kappa. So, therefore, z times this is constant multiplied by dm by dx equal to minus this. But this one kappa is what? Constant. Kappa is a constant now, we got it, yes, constant of integration, function of y and z, function of y and z, it is a, this is a function of x, this is a function, this is a constant, this is all these are constant, and this is z, left hand side z function of x, right hand side what is this? Function of y and z. Now, I think some argument has to be written. So, constant, that constant I am, so constant multiplied by dm by dx, z I am taking on the right hand side equal to minus 1 by z this. So, left hand side is a function of x, right hand side is a function of y and z. Is it possible? See, left hand side is a function of x, right hand side is a function of y and z. Therefore, each side must be a constant, and therefore, dm by dx must be some constant c, and therefore, m, the nature of m is Cx plus constant. So, moment, if you take exact solution, moment, that means that formula sigma equal to mz by I, we have used that formula, the basic flexure formula, that formula will be valid provided m is a linear function, it can be a constant or, so sigma, that means thus the flexure formula sigma x x equal to mz by I will give exact values of sigma x provided m is a constant or a linear function of x. So, this formula will not only give you, even in the case of shear, if the beam is subjected to shear force and bending moment, shear cannot, can shear occur independent of moment and at any cross section? Moment can occur without shear. Can shear occur without moment? I do not think so. Can you have pure shear? Moment will come. Unless there is a rate of change of moment, there cannot be shear. Unless there is a variation of moments. So, we are getting a very good result that yes, this formula is very good and it will give you exact values provided m is constant or a linear function of x. But yes, if it is other things, then it will not give you exact solution. So, this was important because this gives you that what is theory of elasticity. Somebody asked me, I think you asked me yesterday, what is difference between strength of material and theory of elasticity. Theory of elasticity is exact formulation without any assumption. Without any assumptions. Strength of material, we always make some assumptions a priori and simplify the mathematical formulation in order to get approximate solution. So, although this is from, this formula is from strength of material, but even for these two conditions it gives you exact. So, this is the basic, so this is a important revelation, and when now there are two things that I have not been able to cover. More or less I have, there is something called I mean, I must have the name of Saint Venant you have heard, Saint Venant, Prandtl and Saint Venant. I mean, there are two approaches, but Saint Venant, we always say Saint Venant principle. So, there is something called Saint Venant's principle, Saint, S-A-I-N-T, Saint, and it is written in brief, in short, Saint dot, Saint, Saint Venant, V-E-N-A. What is this principle? Somebody will tell me, what is Saint Venant's principle? It is a philosophical principle, but still we should know. In theory of velocity, there is no concept of concentrated moment, concentrated P, etc. It is always stress distribution over a small area. So, P will come, a constant force will come out of distribution of some force. If you take a resultant of that distribution, that will be equal to P. Similarly, distribution of stress will give you a moment. But then in strength of material and in rigid body mechanics, we always talk about force and moment and not distribution. So, Saint Venant's principle is simple in concept, I am just telling you. Wherever you apply a concentrated moment force, see close to that, in the vicinity of that, your stress distribution will be very disturbed. It is difficult to, because you are not giving distribution, you have given equivalent force. So, stress distribution will be there, but that stress distribution will be disturbed, but away from it the stress distribution will be more or less uniform. So, it is very difficult to get the nature of stresses close to the concentrated force or close to concentrated moment, but away from it distribution will stabilize and it will become uniform. So, please, this is in simple words I am trying to. So, for example, if you apply a load, so load actually will be over a small area some distribution. And this, if you apply this stress, then it will be all right, but then we always say point load. Now, point load has no because we never talked about point load in elasticity, has no role to play in elasticity, while in actual practice we always say point load. So, for example, moment, when we say moment, this moment will be given by a stress distribution like this over some depth. This is so Saint Venant simply said that all that in strength of material that you are doing, those results are true in a region which is away from the point of application. What is this? All the formula etc. that you derive in case of strength of material, they are valid for regions away from point of application, not exactly at that point. If you say what is the stress at this point, I cannot say. Okay. Actually, stress distribution, if it is a P, here it will be a bulb like this. maximum stress will be, then it will go. You can assume also like this. So, I do not know what it will be. So, please read in every book, there will be a small. So, please read in every book on theory of velocity, there will be a small half a page description about Saint Venant. Read it once or twice and try to assimilate that, because that is very important in mechanics. And the other concept is uniqueness, uniqueness theorem. Uniqueness theorem in theory of elasticity. See, whatever is stresses and displacements and strains that you are getting is unique, but you have to prove this. Unique means it is not that you will get multiple solutions. There is only one solution to your problem. So, whatever problem is there in mechanics, in physics, there is only one solution exists. There are many problems in where does multiple solutions exist? There are many situations, but not in mechanics. All problems in mechanics have unique solution. So, if the solution is 0.406, it has to be 0.406. Okay. Now, which are the situations where you must have real, yes, eigenvalue, yes, very good. Eigenvalue problem, you have so many solutions depending upon, basically to change the condition you will get a slight eigenvalue problem is there. Why do you get in eigenvalue problem? See, if you see the eigenvalue problem always defined by homogeneous differential equation. Homogeneous means all the derivatives will be there on one side, right hand side non-homogeneous term is 0. It is homogeneous. When this is transformed into algebraic equation, then again you will get a system of equations which will be, let us say, n variable. So, you will get n equations in n variable with right hand side 0. So, it is like A is a coefficient matrix multiplied by x equal to 0. Ax equal to 0 does not give you unique solution. The condition is the determinant of A should be equal to 0. First condition is for this to have a, and then x will always be relative. You can now write down n minus 1 equations in terms of one unknown, and then that means it will go on the right hand side. Then you can solve in terms of that one unknown. Out of n unknown you choose one, and in terms of that you please write n minus 1 equations, and then you solve. So, your equation turns into Ax equal to b. Once it turns Ax equal to b, then A determinant should not, this A reduced A, now it is n minus 1 A, earlier it was n. So, I mean sorry, n by n, there A has to be, determinant of A has to be 0, condition is. Here reduced A, determinant does not have to be 0. If it is 0, then you do not get solution. So, it has to be determinant non-zero, and then you can get solution. So, you are getting all your n minus 1 solution in terms of one unknown, and one unknown can be set anything. So, you will get all relative values. So, eigenvalue problem is this. Other problem in nature that we get, nature means sorry, in real world. So, you must have heard about how many people have heard about operations research, OR problems, and OR problem, one of the ways in which OR operations research problems are defined is by linear programming. These are techniques one should know. In a OR problem, when you go to industrial engineering, you always have to you have got n variables and there are so many conditions involving n. So, that will be written in x plus y plus z equal to something something something, and then you are also interested because your equations are not matching with number of unknowns, they will never match. Number of unknowns, number of equations will never match, either they will be more or they will be less. Therefore, you cannot get. Then they try to find out, okay, let us get a solution of this imperfect equation set subject to some condition, subject to some, I must get the weight of this structure to be minimum, or I must get profit to be maximum. My profit in the industry or in the product manufacture must be minimum. So, you construct a function which is involving profit. So, subject to, so you try to optimize, it is called optimization problem. Optimize a function, get maxima or minima of this function means profit or weight or cost, anything. Optimize that subject to so many conditions. Okay. They will, conditions will never be equal to 0. Some can be 0, but some will also be less than or equal to something. So, such a problem is called optimization problem, and there is a whole range of mathematics. I think if you get an opportunity, please learn a course on optimization. If mechanical engineering is giving that course, please take it. It is, it opens your mind, you know. So, please, and it is very useful, optimization, and it has got applications in structures and in mechanics. It was a very hot topic in around 1965 to 75, 10 years. It was very people were pursuing this subject with lot of vigor, but later on it went down because the solution, you get solution, but the cost of this solution, in order to get the solution, the effort involved is too much. So, people said instead of going through this process, why not get some 10 solutions out of my, based upon my practice, I mean my own judgment. See, there are n equations and there are less than n unknowns or more than n unknowns equations. So, try to solve that imperfect system with something and get some solutions and choose one amongst that. So, instead of, so anyway, so please read this. So, this uniqueness theorem is how to prove that the problem or the solution that we get in this theory of velocity is unique. So, there is a very simple proof I have not covered. Again, it is given in every book on elasticity, please read it. And so, this I will come to an end because today is the last day. So, please, so hopefully this will help you in your life, and then I wish you all the best, do well in life, more than in the course.